Hi, my name is Sadie, and this is the experimental study on the effects of excess nutrients on Anthozoa reducing coral bleaching. So our problem is that coral bleaching is a global issue that leads to our coral reefs dying and endangering species in the ocean. So corals, also known as Anthozoa, are made out of tiny organisms called polyps. They occupy our ocean reefs. They are important as they create habitats and food for millions of species and fish, protecting coastlines from sea wave storms and producing oxygen. Corals and algae have a symbiotic relationship where the corals are the protective habitat for the algae. However, when coral bleaching occurs due to thermal stress events, rising sea temperatures, nutrient ratios, and light availability, etc., the relationship between the photosynthetic symbionts is disrupted and the corals eject the algae. This causes corals to lose their vibrant color and bleach by turning white. Corals have a large impact in the environment because without coral reefs, we could lose as much as half of the oxygen on Earth. And marine species rely on corals for shelter and food source. So in one of the three different types of algae we use ectocarpus because brown algae are known to have very high productivity and they're estimated to absorb 1 gigaton or 1 billion tons of carbon from the atmosphere every year. Basically, if we give CO2 to the brown algae, then out of all the different types of algae used in this experiment, then they will be absorbing the CO2 better and make more nutrients for the corals, and that will help with the tissue growth of the corals because there's some studies that show that the increase of tissue thickness of the coral will lead to a resilience to coral bleaching. So our methodology is to prepare for the experiments, 3 tanks and a control tank were set up with 2,600 milliliters of water. For the independent variable, large amounts of algae were cultivated of the following different types: Amphidium, which is the dinoflagellate, Cladophora, which is the green algae, Ectocarpus, which is the brown algae, and those are the independent variables in the 3 different tanks. To simulate the environment, 50 milliliters of seawater medium was added to each of the water tanks. Then 5 milliliters of nitrate was added to the tanks to promote faster growth for the algae. And eventually we stopped giving them nitrate to avoid algae blooms from developing because they can become very toxic to the corals because of algae blooms. Additionally, 2 milliliters of nitrates and 56 milliliters of saltwater medium were added to all the tanks to keep them alive. For the control group, a mixture of small pieces of the 3 different types of algae was put into the control group with 5 milliliters of nitrate added in, but with no excess carbon dioxide present. The coral we use in this experiment is Pompomsenia or Senia umbellata because it recurrently showed resistance to warming. High water flow or low water flow does not affect the growth of the Pompomsenia. Unlike other soft corals, Pompomsenia is not poisonous. Pompomsenia needs blue light, seawater, and a temperature around 25.5 Celsius to 26 Celsius. The Pompomsenia length of growth was measured with a ruler at the start and at the end of the experiment, and then was placed inside all 4 tanks on top of a rock with blue light in the background. In the experimental group water tanks, we gave an excess amount of 10 grams of carbon dioxide, which is our excess nutrients, to the algae. The pH and temperature of the tanks were recorded daily, and the corals were observed under the microscope to determine any changes in their physical features. The level of absorption was then recorded from a spectrophotometer after the experiment to indicate which type of algae best absorbs sunlight to create nutrients for the coral. So, as you can see, this is the results and discussion. So for our tank 1 with the Amphidium, it had 1 stalk only with 5 millimeters of length, and after the experiment, after we added the whole carbon dioxide in, it became 3 millimeters, so it decreased in growth. So in tank 2, which is the Cladophora, the pom-pom zinnia, it had 5mm with 3 stalks, and after the experiment it had 4 stalks, so it grew more stalks, and it had an increase of growth of 1.5 centimeter growth size. In tank 3, the ectocarpus, which is the brown algae, it had 5mm with 1 stalk only, and at the end of the experiment it had 2 stalks, and it grew into 1 centimeter after the experiment. In the control tank, which is the mix of all the different types of algae, it had growth, like from the beginning of the experiment, it had 5mm with 1 stalk. After the experiment, it's actually very interesting because it had 4 stalks after the end, and it grew to 8mm. But the thing is, it showed signs of coral bleaching. As you can see, it looks like it ejected the algae out of the corals, and see, it turned to white, which shows coral bleaching. For the figures, all the pH and the temperature stayed the same, mostly with the pH ranging from 5 to 7, and temperatures within 23 Celsius to 20 Celsius. But after we added the CO2, the temperatures have dropped. All the tanks in the had mostly consistent pH levels throughout this experiment, and it went from like pH of 5 to 6. However, there was an instance where there was a slight increase in the pH on December 20th from all tanks to like a pH of 7. All the temperature levels were mostly consistent throughout this experiment, with 22 Celsius to 23 Celsius. And on December 8th, there was a drop in temperature from all tanks from 21 to 22 Celsius to 20 Celsius. Not a significant drop, but there is still a drop. After taking 3 readings of the absorbency levels of the algae, as you can see here, we averaged that the absorbance level of the Amphibium had 0.153, which is the absorbency level. Cladophora had 0.225, Ectocarpus had 0.106, and tank 4, which is the control, had 0.113. The Cladophora is 0.225, is like significant here because the absorbency level of the other algae that were used had like the most absorbency level than the other different types of algae. And this means that the higher the absorbance level of the algae, the more light and carbon dioxide of the chlorophyll in the algae can absorb. Meaning, out of all the different algae, Cladophora provided the most nutrients to corals because the coral growth was 1.5 centimeter. Although Amphibium's absorbency level is 0.153, the coral size decreased, which could indicate that the carbon dioxide or thermal stress negatively affected its growth, and the algae did not fortify the coral to regain its lost tissues. Overall, tank 2 had the greatest absorbance value with an average of 0.225, which means that the Cladophora had the best algae type to absorb sunlight to create nutrients for the Anthozoa, which correlates to the data of the growth of the coral in the experiment. Tank 3 had the least absorbance value with an average of 0.106, and the growth of the coral, pom-pom zinnia, grew at different rates with each coral. We could definitely see here that the Cladophora had the most growth, with the length growing from 5mm to 1.5 centimeter, and it even grew like 4 stalks, which is significant here. And in the conclusions, the coral in the control tank experience coral bleaching, which may be due to the mixture of algae being expelled from the Pompomsenia, and we could improve this experiment by containing 3 control tanks with each of the algae, and to see if there would still be coral bleaching. To make this study more accurate, we could use 3D scanning to highlight the entire coral fragment, and future research could be on the effects of different types of carbon dioxide levels on algae. This data could be useful for researchers who are studying the effects of coral bleaching and global warming, and provide information on which algae and corals are best for growth. Thank you so much.